Hi everyone. We're in Chapter 7, Electricity and Electrical Safety, and in this section, 7-2, we're going to talk about outline electrical theory. Have you guys ever noticed lightning on a stormy night? What you see is the effects of electricity. If you plug in a poorly wired appliance and sparks fly everywhere, what you see is the effects of electricity. But you're not really seeing electricity. Instead, you guys are seeing the visual effects on the surrounding air. So electricity does not occupy space or have mass, which is weight, so it is not matter. So electricity is not matter. Okay? Well, if it isn't matter, what is it? Well, electricity is the movement of electrons from one atom to another along a conductor. So here we have atom 1, atom 2, and atom 3. And it is the movement of electrons from each atom. So that's what electricity is. And it's along a conductor, such as a copper wire. So electricity really is just a form of energy, and when in motion, it exhibits magnetic, chemical, and thermal effects. So an electric current, that is the flow of electricity along a conductor. All materials can be classified as either conductors or non-conductors, depending on the ease of which the electric current can be transmitted through them. So what is a conductor? Well, a conductor is a material that conducts electricity. Most metals are really good conductors. Here I drew a copper atom. And if you notice, this outer shell is called the valence shell. And it only has one electron in there. So therefore, it can either easily displace that electron or add more to it. Okay, so therefore, its current can pass easily through that. So copper is a really good conductor, and we find it in our electric wiring and electric motors. Now, pure water, which is distilled, is a poor conductor. Why? Because all the ions are out of it. But if you think of your tap water or a lake or a river, they're really good conductors. Why? Because they have ions in there. Think of your tap water. There's fluoride, calcium, and other things in there. So those are ions. So that explains why we shouldn't go swimming in a lake during an electrical storm. All right, so a non-conductor is known as an insulator. And it is a material that does not easily transmit electricity. So here I put a non-conductor or insulator. And if you notice this valence shell, the outer shell again, it is almost full of electrons. When they have 5 or more, it's a very, very good insulator, and it will not transmit electricity because there's not very much room to add more electrons on there. So what are really good non-conductors? Well, rubber, silk, wood, glass, cement, ceramic, those are all really good insulators. Now when you look at the, say, electric fence and you see those little glass or ceramic little things on the wires, those are good insulators. Look at the telephone poles. You see the glass or those ceramic things up on the wires? Well, those are good insulators. Now, electric wires are composed of metal threads, the conductor, and they are covered with rubber or plastic coating. So those are the non-conductors or the insulators. So think of an old sewing machine. Have you ever seen really old ones and they have like a fabric around the wires? Well, that's usually silk because it is a good insulator or non-conductor. Now, a complete electric circuit, that is the path that the negative and the positive electric currents take from the generating source through the conductors and back to the generating source. Okay, so now we're going to talk about two types of electric current. So there's two types of electric current, and I put them up here: direct current and alternating current. So direct current is abbreviated DC, and what that means is the flow or the current travels in only one direction, and it is produced by chemical means. So I put here the flow goes from A to B, only one direction. Okay? Flashlights, cell phones, cordless tools, they all use direct current produced by the batteries. The battery in your car, that stores electric energy. Without it, your car wouldn't start. Now, an inverter, that's just an apparatus that changes direct current into alternating current. Inverters usually have a plug and a cord, and they allow you to use appliances outside of your salon or spa or your home that would normally be plugged into your wall outlet. A phone charger, that's a really good example of an inverter. So now let's talk about alternating current. Alternating current is abbreviated as AC, and this one, the current flows one direction and then comes back to the other and then flows back. So I drew that on here, goes from A to B, B to A, and then A to B again. So the flow goes back and forth, and it changes direction 60 times a second. Okay, corded hair dryers, curling irons, electric files, table lamps that plug into the outlet, they use alternating current. Now a rectifier, that's an apparatus that will change alternating current into direct current. Cordless electric clippers, phone chargers, they all use a rectifier to change the alternating current from your electrical outlet to DC needed to charge their batteries. So we're going to take a look at the difference between direct current and alternating current. So here we can see direct current, and direct current is the constant, even flow, and it travels in one direction, and it is produced by chemical means. Well, let's look at alternating current. Alternating current is the rapid and interrupted flow. It does travel in two directions, and it is produced by mechanical means. So now we're going to talk about the flow of electric current. It can be compared to water flowing through a hose. Now, if I don't turn on the hose, there's no pressure. Well, there is no water, and the same with electric current. There's no flow. So I've got some terms for you. A volt. A volt is abbreviated with V, and its voltage is what it's known as. It's the unit that measures the force or the pressure push of electric current forward through a conductor. So I always think of it this way: volt, push. Okay. So car batteries, those are 12 volts. Normal electric wall sockets that power your tools, they are 120 volts. Most air conditioners and clothes dryers, they run on 240 volts. A higher voltage indicates way more power. So think about your dryer. Your dryer, if you've ever looked at the plug, it's pretty large. It's way different than what you plug your curling iron into. And your stove, same way. Now an ampere, let's look at that term. An ampere is abbreviated by A, and it is also known as amps. And it is the unit that measures the strength of an electric current. Okay, so just as the hose has to be large enough to carry the amount of water flowing through it, well, a wire is the same way. It's got to be large enough to carry the amount of electricity, the amps, flowing through it. A hair dryer is rated as 12 amps, and it has to have a cord twice as thick as the one rated as 6 amps. Otherwise, your cord would overheat and you'd start a fire. The higher the amp rating, that indicates the greater the number of electrons and a much stronger current. Okay, so let's look at the term milliampere. Okay, so milliampere is abbreviated as MA, and it is 1 to 1,000 of an ampere. It's the current we use in facial and scalp treatments. It's measured in milliamperes, and an ampere current would be way too strong. We wouldn't use that in facial and scalp treatments. An ampere current would damage the skin or the body. So let's look at the term ohm. Ohm is abbreviated as O, and it is a unit that measures the resistance of electric current. So current will not flow through a conductor unless you have force, volts, if they're stronger than the resistance, the ohms. I think of ohms like this. If you're under a lot of stress, you want to ohm out and resist the stress. All right, a watt. Okay, so let's look at that word. A watt is abbreviated W, and it is a unit that measures how much electric energy is being used in 1 second. So for instance, a 40-watt light bulb is going to have 40 watts of energy per second. What? So a kilowatt, that is abbreviated as kW, and it is 1,000 watts. So the electricity in your house is measured in kilowatts per hour. Have you ever looked at your electric bill? When you get it, it'll tell you how many kilowatts that you use. Did you know 1,000 watt, 1 kilowatt hairdryer uses 1,000 watts of energy per second? What? 1 kilowatt will power a television for 3 hours, and it'll run a 100-watt light bulb for 12 hours, and it'll keep an electric clock ticking for 3 whole months. Amazing. All right, guys, that's the end of my theory for this section. So what I want you to do now is do your check-in questions and define the 2 types of electric current. Also, when you finish that and send that to me, then what I want you guys to do is watch a little video. It's called, Hey, What's Up? And then you're going to do another assignment called Electric Current, and it's a matching assignment. I can't remember how that one works exactly, but anyway, it's just a little matching quiz. And then after that, you're going to do another do section called Electrical Measurements. It's a matching test. And then what you do is you reorder the words on the right side to match the words on the left. Okay, so go ahead and finish all that, and I'll see you in the next section. Bye.